This presentation describes how to create a network model through repeated use of lasso regressions. This table shows how key findings from a chain of 5 lasso regressions. In the first regression, the outcome y is regressed on 2 covariates, exposure and mediator variables. In the next regression, covariate C1 is regressed on no variables at all, as nothing precedes it in time. Same for the covariate C2. In the next regression, exposure X is regressed on covariates and both have non-zero coefficients. In the next regression, the mediator Z is regressed on the 2 covariates and the exposure variable. All 3 variables occur before the mediator, but only the exposure variable has a non-zero coefficient. The covariates coefficients are 0 and not shown. The non-zero coefficients in these 5 regressions are shown in this table. Each of these coefficients indicate an association between the variable and the response variable in the regression equation. That is, the independent variable with a non-zero coefficient is a direct predictor of the response variable in the regression equation. One can drop coefficients if absolute value of the coefficients for standardized variable is less than 0.01 or 0.05, depending on whether the focus will be entirely on strong relations. Also, coefficients that are not clinically meaningful indicate problems in formulating the problem. Here, no coefficients are dropped as all values show strong relations. The R-squared values are shown in the table. Regressions with low R-square values of less than 0.05 are typically ignored, as these models do not explain a great deal of variation beyond random prediction. Here all 5 regressions have a reasonable set of R-squared, so all are kept. To create the network, draw an arc for each non-zero coefficient. For outcome y, we draw an arc going from covariate C1, covariate C2, exposure X, and modifier Z to the outcome y. One arc for each significant non-zero direct predictors of y. The exposure variable X is regressed on covariate C1 and covariate C2, and both are statistically significant and non-zero. An arc is drawn from covariate C1 to exposure, and another arc is drawn from covariate C2 to exposure. The mediator variable Z is regressed on exposure variable X, covariate C1 and covariate C2, but only X is a direct predictor and has a non-zero coefficient in the regression. An arc is drawn from the exposure variable X to the mediator variable Z, but nothing is drawn from covariates to the mediator, as those nodes are related indirectly. The network drawn shows all the discovered associations among the variables. All arcs are directed. The direction is set by going from non-zero independent variables to the response variable. This direction corresponds to the time of occurrence of these variables. The joint distribution of the variables, like the network structure, is also estimated from the regression equations. First, the factorial combination of direct predictors of a variable is created. Here we have 4 variables predicting y. To generate the factorial combination of variables, we will need a table with 2 to the power of 4 rows that is 16 rows of data. In half of the 16 rows, covariate C1 is present and half it is absent. Covariate C2 is present in half of the times when covariate C1 is present and absent in the rest. Similarly, covariate C2 is present in half the time when covariate C1 is absent and C2 is absent in the rest. The same procedure is followed for exposure variable. It is present in half the situations where both C1 and C2 are present, and absent in half the situations where both C1 and C2 are present. The same procedure is followed for the situation where C1 is present but C2 is absent, and so on until all combinations of C1 and C2 have corresponding absent and present of X variable. The procedure is continued until a factorial combination is created by examining all possible combinations of the 4 direct predictors of Y. This table now shows 16 combinations of these 4 factors. Each row corresponds to one combination. The first row shows the combination where all predictors are present. The fourth row shows situations where the 2 predictors are present but exposure 2 covariates are present but the exposure and mediator are absent. The last row shows the situation where none of the predictors are present. The regression equation is used to calculate the probability of the outcome. In logistic regression, this is done as 1 divided by e to the inverse power of regression equation. The intercept is 0.3 and is entered into the equation. The coefficient of C1 is 0.12. If we are evaluating the regression for the first row, then C1 is present and its value is 1. The coefficient for C2 is 0.22. Since we are evaluating the regression for the first row, C2 is present and has the value of 1. The regression is evaluated for all the values in the row, yielding a probability of 0.77. The regression equation is used to calculate the probability of the outcome at every row of the factorial combination of direct predictors of Y. This provides the joint distribution of Y for different values of covariates, exposure, and mediator variables. The network also displays the distribution of Y, showing that on average it occurs 71.5% of time. The regression equation for exposure X is used to calculate the probability of the exposure variable as a function of the 2 direct predictors, C1 and C2. When both covariates are present, the unconditional probability of exposure is calculated from the regression equation to be 0.79 or 79% of time. The conditional probability of exposure given presence of C1 but absence of C2 is calculated to be 73%. Similarly, evaluating the regression equation for each row in the factorial combination of direct predictors of X gives us the values of 62% and 53%. This completes the joint distribution of exposure variable X as a function of its direct predictors. On average, the exposure variable occurs 70.9% of the time, as shown in the network. The regression equation is used to calculate the probability of the covariate C1. There are no direct predictors of this variable, and just the intercept of the regression is used. The calculated marginal probability of occurrence of covariate C1 is 65%, and this is shown in the network node. The regression equation is also used to calculate the probability of occurrence of covariate C2, which, like C1, has no predictor. The intercept is used, and the calculated marginal probability is 70%, which can also be read in the network. The regression equation is also used to calculate the joint distribution of mediator Z. When X is present, this probability is calculated from the regression equation to be 0.78. When X is absent, this probability is calculated to be 61%. When X is absent, the coefficient of X is multiplied by 0 and thus does not affect the regression. The probability is calculated to be 61%. This completes the specification of the joint distribution of the mediator variable, and on average, the mediator variable is present in 73% of occasions. We have learned both the structure and the parameters of the network from its associated lasso regressions. We can now use this network model to make inferences about a variety of situations in which different combinations of variables are present.